Okay, let's find the maximum minimum of this function. When we write this exp, what I mean is that y is x times e to the negative x squared over 4. Okay, so, well, it's continuous function on a closed finite interval, so all we need to do is to find the critical points and evaluate the function at all the critical points and endpoints. Now, to find the critical points, we need to take the derivative. So this is a product, so we take the derivative of the first, which is x, that gives us 1, times the second, which is e to the negative x squared over 4. And then the product rule says, then you take plus the first function, which is x, times the derivative of the second. Now the derivative of negative x squared over 4, the 2 comes down, and you get negative x over 2. So when the 2 hits this 4, it just makes a 2 in the denominator. So we have the derivative of the first times the second, plus the first times the derivative of the second. We have e to some function, so the derivative is e to the function times the derivative of that function in the numerator. That's supposed to be a 4 there. Okay, now we're looking for critical points, places where the derivative is 0 undefined. And so I'm going to factor the function. If I pull out e to the negative x squared over 4, then I have a 1 from the first term and a minus x squared over 2 from the second term. So we want to know where the critical points are. That would be places where the derivative is 0 or undefined, but our derivative is always defined, so we can just focus on places where the derivative is 0. Now, e to the minus x squared over 4 has to be a positive number, so I could divide both sides by it, and I would get 1 minus x squared over 2 equals 0, which would say that 1 is x squared over 2, or 2 is x squared, so x is the plus or minus square root of 2. Those are my two critical points. Now that I have my critical points, since it's on a finite closed interval, I can just find the value of my function at the critical points and the endpoints. So I've got to check negative 3, negative root 2, that's about negative 1.4, and positive root 2, that's about positive 1.4, and my other endpoint is 1. Oops, so I need to check my 1. This one is out of range, right? Because root 2 is beyond the end of this interval, so I don't worry about that one. Okay, so we just want to figure out where's our highest value, where's our lowest value, and y of negative 3 would be negative 3, e to the negative 3 squared is 9, so we get negative 9 fourths. If we plug in root 2, we would have if we plug in negative root 2, we'll have negative root 2 times e to the negative root 2 squared is 2, so we'd have e to the negative 1/2. And we plug in 1, we would have 1 times e to the negative 1/4. So we'd have 1 times e to the negative 1/4. Well, so we've checked my critical points. There was only one critical point in the interval and the two endpoints, negative 3 and 1. And we've found our maximum value because these two are negative. This one's got to be our max. Now we've got to decide which of these is bigger. So what we could do is use our calculator to compute what these values are. So let's take 9 divided by 4, and we'll use the plus minus key to make it negative. And then we'll figure out what e to that number is. So let's see, I got my ln. I had the inverse. Okay, so e to the x. So that's e to the negative 9/4. It's 0.1, and then I'm going to multiply it by negative 3. So times 3 negative. And we get a value of negative 0.31619. So this is about negative 0.3161. Okay. Good. Now, the other one, let's clear this. We need to do negative 1/2, so 0.5, I'll hit the plus minus key to make it negative 0.5, and then I'll do e to the x, and then I'll multiply it by the negative square root of 2. So we'll go times 2, and I need to take a square root here. I don't know if I've got to use that or if there's a square root built in. Oh, yeah. If I hit the inverse. Nope. That one's a cube root key. I'm probably staring straight at it, but okay, so root. Okay, so we got 0.85 in this case, and it's negative. So we have approximately negative 0.85. Alright, whereas this one was negative 0.316. So now we've spotted our minimum value as well. So the minimum value is negative root 2 times e to the negative 1/2 occurs when x equals negative root 2, and the max, which is 1 times e to the negative 1/4, so max of e to the negative 1/4, or that's 1 over the 4th root of e, if you like, occurs when x equals a negative root, or equals 1, right? So when x equals 1, that's how we got that highest value. Now it would be nice to look at the graph of this function. So graphing it, we have this, and we can see, oh, sure enough, there's our min, right? And our max is occurring at this endpoint 1. There's our lowest value, which is occurring at, it's a little more than negative 1.5, which would coincide with our value, which was negative square root of 2. If we remove the domain restriction, then we're not guaranteed that there's an absolute max and an absolute min. There may or may not be. In this case, we could look at the critical points again. Remember, when we found the derivative was 1 minus x squared over 2 times e to the minus x squared over 4. So there were critical points, places where the derivative was 0 in particular, critical points at plus or minus the square root of 2. So if we look at those critical points, think about what happens. Here's the one critical point at negative root 2, and the other one over on the other side of 0 at positive root 2. If we have a number that's between negative root 2 and root 2, when we square it, it will be less than 2. So it'll be positive, it'll be less than 2. So less than 2 divided by 2, that's going to be a positive number that's less than 1. 1 minus less than 1 is going to be positive. So we know in this region the derivative is greater than 0. The function's increasing. We also know right here at 0, just looking at the original function, if you plug in 0, you get 0. Now, at root 2, we know the function's level, and at negative root 2, we know the function's level. So the function must climb from here to here. Now, after root 2, if the number is bigger than root 2, if you square it, you get something more than 2. More than 2 divided by 2 would be more than 1, and 1 minus more than 1 would be overwhelmed and become negative. So we can see the derivative after root 2, the derivative is negative. We also can see from the function that if x is positive, this exponential part is always going to be positive no matter what, and so we'll have a positive times a positive. So the function itself has to stay above the x-axis. So even though it's going down, it's going to have to go down less and less to avoid crossing the x-axis. On the other side over here, if we're to the left of negative root 2, when we square that, we get something bigger than 2, and again, bigger than 2 divided by 2 is bigger than 1. 1 minus bigger than 1 gets overwhelmed and becomes negative. So over on this side, the derivative is negative. That means it's going down. Again, though, if x is negative, we can see that y is going to be a negative number times a positive number. It's got to be negative. So although as we go back, the function is climbing, as we go backwards, it can't cross the x-axis, because when x is negative, it's going to have to stay negative. It can't pop up onto the positive side. So looking at that, then we can tell that root 2 has to be there's an absolute max there, right? So at root 2 we get an absolute max. And the value of that absolute max, if you plug in root 2, you're going to get x, which is root 2. Root 2 squared is 2, so we get root 2 e to the negative 1/2. We have an absolute min, so this occurs at x equals root 2. We have an absolute min of, let's see, if we plug in negative root 2, we get negative root 2, negative root 2 squared, though, is still 2, so we still get e to the negative 1/2. So the absolute min is negative root 2 e to the negative 1/2, and that occurs at x equals negative root 2. So in general, even if it's a continuous function, if it's not on a closed bounded interval, then you're not guaranteed an absolute max or an absolute min. You may or may not. In this case, we do have an absolute max and an absolute min. Kind of fun maybe to look at the graph without those of the function without the restrictions. You can see that verifies the picture that we had. Here was our max. If I draw on the line x equals square root of 2, you can see that's where the max occurs, and we located it by finding critical points. The min we said occurred when x was negative square root of 2, and so there's the min. So by using the derivative, we're able to locate that and actually find out quite a bit about what the graph looked like.